And so what modulation means is what you allow is the amplitude to also be a time-dependent function. Okay? And so then what this does is you can basically take your sine wave and contain it in what's known as an envelope. So here, if a of t was a linear envelope, so a of t would be t, so this would be a line there, or you could have a parabola, t squared. And let's see. And so basically, here's an example of a linear modulated signal. You see, because it's periodic, but the amplitude is getting smaller, right? And then it's getting larger here. And we can contain the entire signal using a line. This is x equals y, and x equals minus y there, right? So we're basically putting the original signal in what's known as an envelope. Here it's a linear envelope. And this is known as modulation. OK, so here's the plots with cosine t, and then we scale the amplitude by t. All right? So this is just another concept that in signal processing that's used, this idea of modulation.
So I want to talk about amplitude modulation. So when you have your AM/FM radio, so AM works by modulating the signal, like your voice signal, onto a carrier wave. So the carrier wave would be something like 740 kilohertz. So you tune to 740 on the AM dial. And what you're doing is you're looking for signals that have that frequency. So you take your data signal, so this is your voice signal that you're broadcasting, and you multiply the data wave by the carrier wave. And what you get is this sort of shape where the signal is oscillating as fast as the carrier wave. That's this fast oscillation. But then there's this slow envelope which is containing the data. So the amplitude of the data is contained in the envelope of the signal. So I'm going to play this. Oops, it's going to sound really bad. So that sounds like an emergency distress type signal. And basically this sort of shape, if you use the product to sum formula, so you're multiplying two cosine functions, you generate these two frequency signals. The conversion, there's also a constant, so you also have the carrier frequency. So this is what it looks like in the frequency domain. For frequency modulation, instead what you're doing, so you have a carrier wave, and this is the data wave that you're trying to encode. Where you have large values for your data wave, you're going to want to have a compressed signal. So you change the frequency instantaneously. So the wave is compressed in frequency, or has a higher frequency where it's positive values, and it has the lowest frequency when it has negative values. And so that's what this particular FM wave sounds like. And you can see that the frequency content is much more complicated for FM waves than for AM waves. So I can play around with some of these other things, and you can get different patterns and different spectra. It sounds somewhat different, but basically you have all of these signals to take the data, which is your voice, and send it as an FM wave. So you'd send it at like 100 megahertz on the FM dial. And then the FM radio's job is to receive this signal and construct back the audio that you want to send. So audio signals are usually from 20 hertz to 20 kilohertz. The carrier signal, FM, is like hundreds of megahertz. And so 100 megahertz, I think it's 88 megahertz to 107.9 megahertz. And so this is the signal that the satellite is sending for the FM, and this is what your radio receiver is receiving, and it needs to convert back and get the audio so that you can listen to music.